then stop. You may do more training. Eventually, you might run the marathon. And I would feel very proud of you even trying and just running the first 2 kilometers. But no one will be very proud of you for hopping in a car, driving to the finish line of the marathon, hopping out and walking across the finish line. Sure, you got there, but you got no benefit from the race, no benefit from the training, no strength from that process. And the same is true of thinking about problems. If I just give you the answer and tell you to remember it, you won't have developed any of that strength in problem solving. And that takes time, like learning to run the marathon. And those are the sorts of skills which are needed in India. They're the sorts of skills which are needed in Australia. They're needed internationally. And they take a slightly different way of working with learners to go and foster those skills. So bear with me tonight if sometimes we don't get an answer and I just leave you with the problem. That's deliberate. That's a good thing. From my point of view, sometimes that's a very good thing. So let's stop with the talking and let's go and see about how we think about things. Now, at the moment, I can see that we've got 37 participants in the Zoom meeting at the moment, which is an interesting number. I noticed that it's prime, but that's not particularly significant for the next activity. If I was going to ask all of you to shake hands with all of the participants, so there are 37 of you, myself, if we were all going to shake hands, how many handshakes would that need, do you think? Put your answer in the chat window. So open up the chat box rather than hopping online, because I'd like to see all of your ideas, not just the first person to speak. So 37 of us, we are all going to shake hands once. How many handshakes in total will we need tonight? Just think about that for a moment. If you need to use a calculator, that's fine. We all have calculators. 70, 37, 70. When you give me your answer, I'm not interested if you're right or wrong. I'm interested in how you got that answer. So someone has offered 70. I'm sort of thinking, how do you get to 70 from 37? Just sort of wondering. It's an interesting number. Normally, I can tell how you think from the answer that you give. 666. That's a very special number in the West. 37, by that, someone has looked at the formulas on there. On that, some of you understand the process. All right. Some of you have just given me the algorithm, which is fantastic. Just, some have multiplied 35 with 2. All right, great. 18 and a half handshakes. That's kind of interesting. 37 times 2 equals 74, minus a few on there. I'll wait a moment for a few more answers to come through. There, 70 and 666. I don't know. I haven't checked the answer, because again, take it. I'm not interested in the answer. I'm interested in how you work out the answer. So one of the things which we need to do in computational thinking is we really need to try and understand the problem. We need to understand the problem. And we also need to think about how this problem might have similarities with other problems. So this idea of handshakes, it's not just about friendship and how long it would take us to shake hands. But in the current world, we have so much relying on digital technologies and communication. And the simplest act of communication actually requires an awful lot of handshakes. So if I just pick up my phone is going to handshake with the mobile phone tower. They're going to handshake with my bank to see if I've got credit. They're going to handshake with a different server. There might be 100 handshakes just before I can make my first phone call. All right, just a digital handshakes, 100 digital handshakes to make a phone call. And so if we're going to be designing communication systems, we need to understand how the number of handshakes changes as our networks get bigger. So there's a billion plus 1.2 billion or 3, I'm not quite sure where it's up to, but about 1 billion people in India. If they were all going to shake hands with each other, that would be 5 with 17 zeros after it, handshakes for everyone in India to shake hands. As society becomes more digital and we get an internet of things, like the fridge is connected to your shoes, is connected to the lights, is connected to, all sorts of things, we may end up with every person having 100 or 1,000 digital devices all shaking hands. And so we need to understand how things like these handshake numbers change as the size of our networks get bigger, because we need to build networks that can handle that amount of traffic. So if everyone in India had to shake hands with each other, that's a lot of handshakes. If everyone could shake hands once a second, how long would it take for all of India to finish shaking hands? So if it was 1 billion people, and they all had to shake hands and they shook hands, one handshake every second, how long would it take to shake hands? The total number of handshakes is 5 with 17 zeros after it. Any guesses on that? I would much rather be doing this face-to-face with everyone in a group. I could see how you were thinking. This seems to be a harder question than the first question about how many handshakes you need for 37 people. I don't know. Is this a harder question? Is this a harder question or not? Or do we just have to think about the problem differently? I was actually doing this afternoon. I was going, yeah, how many handshakes would India need? Going, oh, wow, nice, big number. It's actually a relatively simple question, that one, but we're fooling ourselves, or you're very shy. And I love Indians. They're not normally shy. So I think you're struggling with how do you work this out? Okay, so look, thanks for your answer. Someone's going, all right, 5 to the 10 by 17 seconds. All right, that's an answer. That tells me how Nitish is thinking about the problem. That's if someone's divided there to convert it to hours for me. That's very kind. If I wanted to convert that number to years, it's 31.6 years. But that's not the answer. That's not the answer, because we're all shaking hands at the same time. And so there is 1 billion of us, and I have to shake hands with 1 billion people. So it's going to take 1 billion seconds. Billion minus 1. I don't shake hands with myself. So this is just how we can often get trapped into how we think about problems. Now, I wasn't being deliberately tricky with that, but it's just an example of how sometimes if we're not told what the problem is, we don't always use the right method. And again, that's one of the things which I encourage you to try lots of different problems so you get flexible with how you tackle problems. Let's see if we've loosened you up a bit. Let's see if we've loosened you up at all with that. I'm thinking of a rule. It's a rule which is going to generate a series of numbers, or that can generate a series of numbers. And I will give you some numbers that follow my rule. So these numbers will be evidence, data of what my rule is. Your job, your challenge is you need to try and work out, not guess, you need to try and work out what my rule is, okay? These numbers follow my rule. I've just shared on the chat. These numbers follow my rule. You can ask me if another number follows the rule.
All the numbers are being multiplied by 2.
So the numbers are doubled.
So the numbers are doubled.
Okay, they have. Those numbers have.
So those numbers are doubled when
Yes.
it goes to next.
Yes, sir.
Yep. Yep. That's not my rule. That's not my rule. So you're trying to guess the rule from the numbers. I suggest you try and give me some other numbers and see if they give you more evidence about what the rule is. So yes, those numbers do double, and they could follow the pattern 2 to the power of 0, 1, 2, 3, 4. But that's not my rule. That's not my rule. 2 to the power of n is just a different way of expressing what Amrit suggested. So no, all the numbers are multiplied by 2. No, that's not my rule. So far, everyone has been trying to guess the rule. No one's been trying to test new evidence. All right? So you should try, I suggest, to think of another number and give that to me and see if I tell you that follows the rule or not. So try that. So someone give me another number. 32. 32, if 32 is the next number, that would follow my rule. So that number would follow my rule. And if the next two numbers were 32 and 64, that would follow my rule. But doubling is not my rule, nor is n to the power of 2. So if does the sequence, so someone is saying 256. So if the numbers were 2, 4, 8, 16, 256, that would follow my rule.
Sir?
Yeah.
Sir, I think your rule is a number is added, in a number 3 is added and 1 is subtracted.
So that wouldn't give me that first pattern. That wouldn't give me the first pattern because the difference changes. So someone has asked, does the sequence 1, 3, 9, 27 follow my rule? And the answer is yes. Yes, that follows my rule. What we're experimenting with here is really scientific thinking. Scientific thinking. And often in science, we have a hypothesis and we are tempted as people to try and prove our idea. And so far, you've all leapt to an idea. You've all looked at the pattern, which is good, which is very good. And you think, oh, I see the pattern. The pattern must be the rule. And you keep asking me numbers that follow the rule, but they're not helping you probe, test what the rule is. So, Ipsita, you're putting in a sequence. You're putting in the sequence.
I was trying to, but fine.
That's okay. What's your sequence? Ipsita, what's your suggested sequence that you want to test?
I was wanting to test 1, then 4.
1 and 4 follows my rule. Follows my rule. Duncan has
4,
yeah.
8 and 16.
1, 4, 8 and 16, that follows my rule. We're going to stop in a moment, and that's okay. And you haven't worked out my rule yet. All right, one last experiment about my rule. Has anyone got another number they would like to test? another sequence they would like to test. Because we have so much to get through tonight. But these sessions like this, where you're, I don't know, these are valuable. These are valuable. And many teachers would be worried if the class was sitting there quiet going, I don't know. I don't understand how to work on this. Not all teachers, but some. All right. I hope we have some teachers here tonight. I hope we do. All right. We'll come back to that if you remind me later. So we're going to time out. We're going to time out on that. And what we're going to set up now, we're going to jump around all over the place tonight. I'm going, Spectic has said, does 525, 125, 625 follow my rule? Yes, it does. Yes, it does. Okay, so that follows my rule. So I don't think I'm going to give you a lot of time to keep thinking about that during the rest of the workshop. But if you do, keep thinking about it. We'll come back. What I'm going to ask now is we're going to set up a little experiment, a little activity. And for this, I will need the help of my friends at the Science Centre. So hopefully they've got some playing cards.
Yes, we
there.
do have. We do have.
That is fantastic. So if you can turn on your video.
Yes.
And let's go and spotlight you, make you the hero. So
1 minute. 1 minute.
Yeah. Share your video. We're going to look at something. Hopefully, I haven't tried this online over Zoom, and my friends at the Science Centre haven't been prepared for this, so I haven't told them what we're doing. So we're going to set up an experiment. We're going to set up an activity, and to see whether or not I can actually memorize a very complex pattern. Fantastic. And can we have the camera?
Yes,
That's wonderful. That's wonderful. You're looking splendid, sir, as you always do. And now, can you set? Have you got some playing cards for us today?
Yes, I do have, sir.
That's fantastic. Now, is it possible for us to get the camera to look down at your table so we can see the playing cards on the table?
Yes, let me set it, sir.
That would be great. It's not that looking at you is at all burdensome, but we will need to see the playing cards.
Is it, sir?
Excellent. That's okay.
Yes.
Is it? I'd like you to place the cards out in a 5x5 grid. Okay. So in a kind of a square grid, 5x5, and hopefully when you've got that done, you'll be able to lift your camera up so we can actually see all of the cards at the same time. We can do that once you've got all the cards out.
You mean 5x5, sir?
5x5, so 25 cards.
Yes.
Five in a row, five columns. Now this is something everyone else can do later today, and try it with some of your friends. Just hopefully we can get, when my good friend has put all the cards out, you'll be able to lift them up, lift the camera up so we can see.
5x5.
Yep. All right. So when you've got 25 cards out there in a grid, all right. Now
Can people see?
Now we in a moment or two we can. I'll need to be able to see all of the cards
All
kind of
the cards together.
at
That
once.
camera
Yeah.
can be taken off.
Yep. That's super. Okay, that's going to work. That's going to work just fine. Excellent. Now, what I would like you to do is randomly turn about half of those cards face up. Okay.
Yes.
So just a few cards on each. Just turn those up, kind of at random. And let me know when you've got that done. All right. And at the moment, I'm not looking at what you're setting up. All right. All right. Now, can you just for a moment, just when you've finished?
Yes.
Okay. And if you've stopped?
Yes, I have stopped.
Okay. Then if you just hold the camera still. Okay. I think I'm done. All right. Now just move the camera away so we can't see the cards.
You need to see all the cards, sir.
No, move the camera away now, just so I can't see the cards. All right. So just turn the camera away. We can look at yourself or the walls of the study. I don't mind. Just take the camera off the cards. I don't want to see any of the cards now. Super. All right. Now, I know this is a little cumbersome for you. It would be so much easier if we were doing this before COVID. What I want you to do now is, without telling me, I want you to go and change one of the cards. So if the card, you might choose a card that's facing up. I want you to turn it down. If the card's facing down, you can turn it up, but just change one card. So you're going to toggle one card. Don't show me which one you're doing. It needs to be secret.
Only one, sir?
Just one.
Yes,
just
I
one.
did.
And you've done?
Yes.
Okay. All right. Now just put the camera back so I can see all of the cards again. Okay. All right. And if I know it's a bit, could you just pull back just a little bit? Okay, from my understanding, you changed the card in the bottom left-hand corner.
Yes, sir. You are right. Absolutely right.
Okay, all right. Thanks very much for doing all of that. You changed the card in the bottom corner.
I did this one, sir.
Fantastic. Look, thank you so much for all of the help.
Congratulations, sir.
And it's not me, it's the science. It's the science, but which we're going to look at now. How do people think, and you can put the camera down now. Thanks very much.
Camera down.
Yeah. So how do people think I was able to do that? Now, I didn't take a picture of the cards. How was it that I was able to do that?
Spotlight.
Yeah. How was I able to do that? There was a pattern. I might have recognized something in the pattern. What was it in the pattern of those cards that I was working with, do you think? What do you think it was? I could have easily done that if we were working face to face, or I wanted to put my friend to a lot of work. We could have done a pattern of 64 by 64. He could have changed one card. I would still be able to find it. That would have just been very inconvenient. He would have had to clear his study, and we'd have to put cards all out across the floor, but we could have done it with 64 by 64. Let's just have a think about that for a moment. I'm going to change my camera here over to my workbench so we can look down on my whiteboard, and we'll go and look at remembering. I'm very old. I don't have a good memory. So the chances of me being able to remember all of that with the camera wobbling around, maybe 5 by 5 you could remember in kind of a minute. But as I said, I could do that with 64 by 64 cards. It wouldn't be very much longer. Let me just change camera. All right. So this is now over on the whiteboard. One of the things which in school you will be taught, almost the first thing you'll be taught when you're learning to count, is you'll be taught to count, and you'll be introduced to the idea of odd and even numbers. 3 is odd, 4 is even. And after we've learnt that, we just about never come back in our mathematics to talk about odd and even numbers, as if it doesn't matter. When you start doing computational thinking, odds and evens are very powerful tools, and they are your friends. And so let me just work out where is safe to draw here. Okay. So if I was looking at a 5 by 5 grid, which we were with the cards, and if I'd put one face up, another face up, one face up, these ones face up, and I'd left the pattern at that. One of the things which I can do, and one of the things I did in that activity, was I just looked to go and see which were odd and even filled rows and columns. So this one is even, I didn't do anything. This one is odd, so I just made a mark. This one is odd, I made a mark. This one's even, didn't do anything. This one is odd, it's got 1. Here, this is odd, just 1, odd, even, odd, even. And so I just worked out which rows had odd numbers of cards face up. I could have chosen to count the number of even ones, but you just do 1. Now, if my friend made any change to that, if you put an extra 1 here, if we add 1 to an odd number, it's got to be even. This was odd before, we added 1 to it, it's got to be even now. And so my pattern, when I was looking back at the cards after he'd made the change, I could go, this, oh, hang on, this is even, yes. There are 2 here, oh, this is marked as odd. The change must have happened, 1 in this row has changed. This one's okay, this one's okay, this one's okay, this one's okay. This one is saying this should be odd, but in fact it's even. And so there's a change in this row and there's a change in this row. And so that can be used to tell you where the change is. Now, whilst tonight we might have done that as a kind of a memory trick. I'm not a big fan of memory, or sorry, magic. Big fan of memory, not a fan of magic on there. So I don't set that up as a great magic trick, although it looks like that. How can you do it? It's just using basic science, the most basic of mathematics. Is this important? Well, actually, it's really important. These days, we send lots and lots of data, trillions of bits of information, ones and zeros. If I was going to send you a lot of data and I wanted to make sure you got the data correctly, it wasn't corrupted, nothing dropped out, you got everything. If I sent you a large file, how could I be sure that you got the file I sent? How could you be sure that you received the file without any corruption, without any bits changed in it? Telecommunications is very good, but it makes mistakes. The equipment will make mistakes. It can. People are asking, can it work with 246 cards? Raja, if you got 246 cards, we can do it. Okay, it'll just take a while. It can work with any number of cards. You just remember where the odd, you just number. I choose the odd ones. Which ones rows have odd, which columns have odd. If you send someone a lot of information, like the information contained in that grid, they can be ones and zeros. They can be representations of binary digital information. So if I'm sending you that data, might be a picture, it might be a Word file, it's all ones and zeros. I can take that number, that data, before I send it, and I can go and do that mathematics on it. So I might take a big chunk of that data, 246 cards, Roger, worth of cards of data, and I can go and do odd, even, odd, 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 even, odd. And I can also send to you that number. So I can send you the 5 by 5 cards, but I can also send you the data, which is looking at the odd arrangements, the odd numbers. And then your computer can do just what I did, can look at that data and this check number. It's actually, in computer science, it's called a checksum. It's a checksum. And this sum, this checksum, allows me to check that the data is good. And if the data is wrong, I can actually fix it. I don't have to resend the file. I can go, oh, there's this bit right here that's toggled. It should be the other way around. I'll just fix it. And so this is every time you write data to a CD, you store information on a thumb drive. A computer moves information. You have a digital phone call. You do some of those digital handshakes. This data is collected up and you get a checksum. You get a checksum, which enables the recipient to check that the data came through as it should. There are other variations of that process that you can use to, in fact, fix 1 or 2 or 3 or 4 mistakes all in the one file. And people that do kind of, electronic engineering, communications engineering, that are involved in security and encryption and cybersecurity, they will have ways of correcting that sort of information, but they spend a lot of time working out what is the most efficient way. How can they send the most information, which is most secure, but also if something is changed, how can they fix the greatest number of mistakes? Do they send lots of little files or one big file with one enormous checksum? This is an area of kind of science, computer science and computational thinking, which we don't often hear about, but this is how you use information science to get on with these sorts of things. So a few of you have sort of gone, hey, that's a pretty cool trick. Try it on your friends. It's not magic, it's just applying your good computational thinking to go and get those things sorted out. I'm glad you find that kind of as neat as I do. When I kind of came across that activity, I was going, this is wonderful. It makes so much sense of so many things. Given the time, And I think my friends there suggested they didn't want me to do a 7-hour seminar tonight. They said something silly like 60 minutes. I'm going to jump to a different kind of problem, a different problem. And for that, we'll go back to my work table, and we'll look at some simple problems, but we'll also look at how is it every time we need to have an even number? All you need to do is decide how you're going to do your checksum. So I always just I mark which ones are odd. It'll work just the same if you mark just the even ones. That's the power of odds and evens. Add one, make one change, add one to an even number, it has to be odd. Add one to an odd number, it has to be even. And you were probably 5 the last time you spent any time thinking about odd and even numbers. And then you just left them behind. They're actually really, really important. Let's go back over to the workbench and let's look at, I've got a grid there. Let's look at a related, is it related? Yeah, it's sort of related. A related problem. That's going to take too long. So I've got a clean one just here. So imagine now I've got a grid. So it's a little bit like reverse Sudoku or magic squares. And I know a lot of people in India love kind of magic squares. I kind of see it everywhere in the science centers, which is great. A little bit like that previous checksum problem, and a little bit like your magic squares. Imagine I'm able to look through this square from the edge, and I can't tell where there is an object, but I can tell how many are there. So if I look through here and I go, there is 2. There is 2 somewhere along here. And when I look through here, there is 1. And when I look through here, there is 2. But when I look through here, there is 2. When I look through here, there is 1. When I look through here, there is 2. So I'm not sure where the objects are in this grid, but I know that there are 2 here, and there's 1 somewhere along there, 2 somewhere along here, and likewise in this direction. Can you use that information to reconstruct what the pattern of objects is inside the grid? Just think about that for a moment. Just think about that for a moment. Can you...
Sir, I found the
Yes, sir. Sir, may I speak?
Yes, sir.
Yes, sure. Just one at a time. Yeah.
So if we see, we got the same pattern on both rows and columns. For example, we can take the 2. Now, we go horizontally. For example, we consider the last 2 of the 2, 1, 2 vertically. So now we also observe that there is a 2 on the horizontal side. So if we draw lines from both the 2s, they will intersect at one square, and there we can say that there is one object. Now also we see that there's another 2. So now if we take the other 2 from the horizontal side and another one from the vertical side, they will also intersect at a common point, and there we can say that there's the second object. And similarly, if we go with the 1, we can see that they intersect at the square number 5. So we can say that that object is at square number 5. Similarly, it will work for everything.
So what is the pattern? Just tell me which squares to put a mark in to suggest that there is an
5.
object there.
Sir, can I tell
Yep.
the
So
answer?
5 first of all, and then we have 3,
3, 5, 7, 9.
3, and we have 9,
The 7. The 7.
and we yes.
The 1.
So one, two, one.
Okay. All right. Okay. We got there.
But
All right.
I got another answer.
There's another answer. What's
Yes.
the other option?
The other option is if I fill in the gaps of the boxes 2 and 3,
Yeah.
and then the box 4,
Yeah.
and then box 7, 8, 9. 8 and 9.
Yeah. So it gives me two.
So it becomes 3 objects.
This gives me 2, 2, 2, not 2, 1, 2. All right. But that's okay. What you're looking at is how to think about this problem. I keep saying it, but I really don't mind. I really don't mind if you get the wrong answer, provided you're trying to work it out. That's what builds up your strength. Making mistakes is very powerful learning. All right. It's not something to be worried about. Not learning from your mistakes, that's a problem. But making mistakes, make lots, make them quickly and learn from them.
So I have another pattern.
You have another pattern, yeah?
Yes, sir. So my pattern is that on I have an object on first square 1.
4 square, yeah?
No, sir. So in 1.
Just in one? Let me make this nice and clean for you. He says, making a mess. All right. So one in as in one.
1,
Yep.
2.
Yep.
6.
Yep.
7. 9.
Does that work, everyone? That was the original pattern. 2, 1, 2, 2, 1, 2. Is that there? That was the original pattern.
Sir.
Yeah.
Yes, sir.
It is. It is.
That's good.
So it didn't have a unique solution. Didn't have a unique solution.
Could have been anything.
Sometimes it will. Sometimes with these simple small squares, it won't. I'm going to, before we finish tonight, share out with you via Zoom, hopefully some files of some challenging activities for you to do, complex versions of these squares. So you can actually, perhaps if you've got some friends, make some of these and share them with each other. What now if I gave you this grid? If I gave you this grid and gave you numbers, and don't write that down because I just made that up. But what if I gave you that grid and I told you that you could put 2 crosses in 1 square? So you could have denser squares. So that would still give you 3. So imagine I gave you those rules, all right? And a problem this big, how do you think you would try and solve that? With that small grid I gave you, you were kind of using intuition, using some ideas about which parts you could be more certain about, like where the 1 and the 1 indicated. There had to be just a 1 there somewhere. How would you write a program to try and solve this grid? Because these days, in hospitals all over the planet, we have machines that we use to solve this problem all the time. They're fairly expensive machines. Things like all those things which are CAT scanners or MRI, all these biomedical imaging machines. A biomedical imaging machine, all it can do is to look through the side of your body with a series of rays and work out how much of that ray is absorbed. So it can't see inside your body. It just looks through and says there's a lot of material here, not so much here, some here, and they move and they do that not just this way and that way, but they do it this way and then this way, then on the diagonals. They get a whole set of numbers for the diagonals, and they actually use the computational science to take those numbers and work backwards to fill in all of those squares. And that's how you get CAT scans, which is computer-aided tomography. The computers are looking at these numbers and rebuilding the images, just as you did with the simple 9 squares. This one would be challenging for you, but you could probably do it. It's like a horrible Sudoku for the weekend. But in a CAT scan, they might have billions of these squares to go and try and work out. So don't try and solve that one. I can give you some other ones to try and solve yourselves. But the idea of computational thinking and odds and evens has its strength as a career in coming up with the techniques to go and solve those problems. If you can solve those sorts of problems, work out how to look at those numbers and get back to the image, then you make powerful technology that can help heal people. You'll also have a great career and probably be very rich, but you'll be doing things which are actually helping people, making new technologies. Let's come back here now. So does that kind of look interesting? Did you ever think about how the nature of odds and evens and mathematics is one of the things which kind of really needs to be solved? Those problems need to be solved to give us those sorts of technologies.
I never paid so much attention to that.
Yeah, it's I can do those puzzles on the board there, but when I think about how smart, how powerful.
So your voice is not audible.
Sorry, not audible?
No, sir. I think there's some problem with his network.
Yeah, I'm coming through. So if you can't hear me, the problem's at your end. I'm sorry. So yeah, just how these insights, how do you automate? How do you automate what you did with that 3x3 to then go and work on a problem which has got thousands of grids, cells, 1,000 this way, 1,000 that way? How do you do that? How do you do that? So that's kind of where I get excited about mathematics. And I go, I'd like to try and write a small program to do that myself. And I just play recreationally with those sorts of things. Because you look at it at the 3x3 and go, oh, it's like noughts and crosses. This shouldn't be too hard to solve, until you suddenly get a large set of numbers and you're going, this needs me to think about it in a different way. So with that, we're going to look at another problem. In pretty much wherever I go around the world in many different places. Most places that I go, I will talk about some game or something which I will say someone invented, and they will then tell me that, oh, no, sir, you're wrong. No, we invented that here. So I'm not going to make that mistake tonight. So India invented chess. Okay, we all know that. And many Indians love the game of chess. Lots of students love to play it. You're very passionate about those sorts of games. In Australia, we've got great weather. We don't stay inside so much, so we're not so good at chess. So we have a simpler version of chess here in Australia. but it's still a little tricky, but it's one which I think you'll be able to work out. It may take a little bit of time. So let's just go back to my work table with this. In Australia, we have a very special kind of chessboard. And it's pretty much shaped just like this. And we'll number it 1, 2, 3. Hopefully you can read those numbers. And that's the chessboard. That's the chessboard that we use. It's a little bit smaller and a different shape to yours. And we also just have the one chess piece. And the chess piece that we have is the knight, or you might call it the horse, but I think you would probably call it the knight. And the knight kind of moves in an interesting way. I'm sure everyone here tonight will know which way the knight moves. Kind of moves in an L. So 1 by 2, 2 by 1. So what I'm going to challenge you to tackle tonight is to go and start with the knight in square 1, and I want you to take it on a tour. And in this kind of mathematics, tour has a special meaning. It means you're going to visit every square once, only once, and on your last move, come back to the beginning. So when a knight goes from 1, it can go 2 and 1, so it can go from 1 to 7. That doesn't mean it's gone through 4 and 8. It's kind of like Doctor Who, it teleports, all right? If on a chessboard, if you had other pieces here, the knight could still get to 7. So if I started on 1, I could get to 7 or 9 or 6 even, all right? So make a small drawing of that, or just look at it on the screen if you've got good working memory.
Sir?
And I want you to see if you can go on a tour to visit every square once, land on every square once and only once, and on your last move, come back to square 1. So give that a try.
What is this game called?
Well, this is just the next challenge I'm giving you. So I don't need to give it a name, because again, if I give it a name, you might be tempted to Google the name and find the answer, and that would be just like driving your car to the end of the marathon. And that would not be worth doing. So have a try at that problem. I have had one child in Kolkata, would have been about 10-year-old, finish this in about 40 seconds. Probably the fastest I've ever seen. I'll give you a few minutes to work on it. Keep track of which numbers you've landed on, which order. How are we going with that? How are we going? I'll give you a few minutes. All right, how are we going? I sometimes tell people I can solve any problem. I can solve any problem except time. So we're going to, if no one's got an answer at the moment, that's okay. No one's got an answer at the moment. We'll stop and let's try a different problem. We'll see how you go with this. So here's a different problem. So here is a town. Here's a town, and it's got a number of organizations, museums, art galleries, zoos, and aquariums that you would like to visit. And so this is also a tour problem. We're going to start here. And for this particular problem, you also need to do a tour. So you need to start here. You need to visit every destination. These circles are destinations on a tourist map. You need to visit all of them. You need to visit all of them once and only once. And on your final leg, come back to the start. You might not use all of the roads, but you need to go through all of the points. You can't go through any point twice. So have a look at that problem and see how you go. Try that problem.
Sir?
Yeah.
Sir, I think it will be better if you number the dots.
I can do that for you. Let me how would you like to number them? This way? Number 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. That'll help you tell me which path you might be trying.
So how many steps should we skip each time?
It's not a case of skipping. You need to tell me how you're going to go and join, how you're going to go through all of the dots once and only once, following these roads. The straight lines are the roads. So you need to get from 1 to visit all of these dots once and only once, and on the final be able to come back to the start.
Sir, can I tell about that?
Sure. If you've got what you think is a solution, which path did you choose?
Sir, starting from 1 to 8.
Yep. Let me get a different colored pen so everyone can see what you're suggesting. Yep. So 1 to 8.
Then 9.
Yep.
10.
Yep.
11.
Yep.
12.
Yep.
7.
Yep.
6.
Yep.
5.
Yep.
4.
Yep.
3.
Yep.
2.
Yep. And the last move.
1.
Back to 1. Excellent. Well done. Did that one feel a lot easier than the chess problem?
Yes, sir.
Yeah.
Yes, sir. Yes, sir.
The thing is, we got some interesting series of numbers coming in there, which I'll have to check. Can anyone see a different solution here? So that certainly works. Well done. Any other
sir.
solutions?
Sir,
Yes?
Yes,
I
yes,
can
sir.
speak.
Sir, I
Sir,
can speak. Yes, sir.
Sir, we have to start from 1
Yes.
to 2.
Yeah.
Sir, exactly the reverse solution of this one can
Sure.
be.
Yeah. So this is 1 to 2. We could solve it going the other way, 1 to 8 and around. So that's one solution, 2 solutions. Are there any other solutions?
So starting from 1 to 2 to 3 to 4 to 5 to 6, then 7, 8, 9, 10, 11, and then no.
Then we're in trouble.
Yes,
I
sir.
think I think we have some other solutions though. Now let me just do something a little tricky. All right. This problem, which you're looking at now, in fact, is not easier than the chess problem. Okay. This problem, which you're looking at here, is the chess problem. I've just drawn it slightly differently. And so this is one of the things which sometimes you've been working on a problem at school or home and you're stuck. And someone trying to help you says, you should look at the problem slightly differently. Now that's good advice.
Sir, I found.
That's all right. We'll come back to your extra solution in just a moment. I'm glad you got there. I'm glad you got there. They will suggest that maybe you should look at the problem in a different way. Good advice, but what does that mean? This is the chess problem. This is actually a map of all of the connections in the chess problem. The chess problem doesn't really rely on the geography, doesn't rely on the shape of that puzzle. The important thing to solve that problem is how those bits are connected by the strange movement of the knight. So if I look at this, the 1 connects to 7, 9, and 6. So 1 connects to 7, 9, and 6. So if I put 1 connects to 7, 9, and 6. 9 connects to 1. 9 also connects to 3, but doesn't connect to anything else. So 9 connects to 3. 3 connects to 2 and 9 and 11. So 3 connects to 2, 9, and 11. 2 connects to 8. And so we're just drawing the map of the connections, all right? 2 connects to 8 and 10, and 3 means that one's 10. This one's 5, this one's 4, this one's 12. So now we've actually just drawn a map of the connections, all right? Here, when we're trying to solve this problem, we've got to remember the past, where the moves were, and think about the future. And that's very hard for us to visualize, to get a picture of what that would look like. And that makes solving this problem this way very hard. If I take the connections and make a map of the problem, it looks like this. And many of you found it easy to solve. I'm going to go around here. There's one. Okay. I think that one might have been slightly different even to one of the others. It doesn't matter. But you can use your visual processing, your eyesight, how your brain handles space to go and solve that problem. You just look at it and going, oh yeah,
Now it's done.
It's done. And now, once you've made the map, you can use the map to go and work out the path from here. So I will take this path and take those numbers and see if that solves our knight's tour. So 1 to 9 to 3 to 2 to 8 to 6, to 12, to 4, to 10, to 11, to 5, to 7, to 1. And we're done. And if you can look at this and find 2, 3, or 4 different solutions, you can just run off those numbers and use it here. Now, looking at this, you're happy to think about, are there other solutions? You can look at it and going, this way, reverse, left, right, swap that. Does that give me a different pattern? That's easy. If I asked you to tell me how many different solutions there are to this, you wouldn't even know where to start in answering that question. Answering the question about how many different solutions. It's hard enough to find one. You don't know if you're going to be able to find more, and you won't know when you've finished finding all of the ones that are there. Hopefully that sort of gives you some, kind of interesting examples, some concrete examples about sometimes when we're thinking about problems in space or time, that we can kind of make a map of them. Don't think about them in a sequence. Let's draw the sequence out. Let's make a map of the problem. You can use different parts of your brain. Our kind of working memory, kind of how many bits of information we can remember at once. It's about 5, maybe 10. You can look at 100 bits of a puzzle visually and see where the bits connect. You can do that easily. Our visual processing is enormous. Our working is really quite small. So using tricks like that, approaches like that, actually can give us some very powerful ways to think about maths, to think about problems. Now, I'm just going to check in with our hosts at this point. How are we going for time? Do we need to wrap up tonight's session there, or have we got a little bit more time? I'll just wait to hear back from our hosts.
Dr. Stuart?
Yeah.
Everybody was happy, thinking round the clock. What is the key with you? They do not understand.
I hope I've left them with some questions to keep them busy.
Yes.
And if some of these participants are back tomorrow night, maybe they can bring some more answers back tomorrow night.
Exactly, sir. Actually, I wish my whole heart towards you for sacrificing, for dedicating your brain towards the development of the whole world together is your attitude. Thank you, sir. Namaste.
My complete pleasure.
So children, participants, students, teachers, I hope you have enjoyed to your fullest extent. If you are happy, then write down in the chat box, yes, sir, thumbs up, so that Dr. Stuart will be aware that our students in India and teachers in India are proud to join with him, at least today's session. Then I announce again tomorrow and the day after tomorrow, the same time, you will be joining again with Dr. Stuart with the different topics. Yes, sir. Sir, could you notice?
I certainly
Did you
can.
notice? Everybody is satisfied.
We just should have had 4 more hours. That's all.
Yes. So also myself, now on behalf of Regional Science Center Bhubaneshwar and Odisha Vigyan Academy, at the same time, I wish you, sir, a very, very, very comfortable life ahead for all of us. And thank you so much. Thank you, children. Thank you, teachers, for being with us. Next time, next day, same time, again we meet Dr. Stuart again. Thank you, sir.
Indeed. Thank you.
To an end.
Thank you, sir.